Hello everyone, my name is Imam Nurbani Yusuf. Today, I shall present our paper titled Accurate Generation of Trigger Action Programs with Domain-Adapted Sequence-to-Sequence Learning. Steps are event-driven rules used to automate smart devices or internet services. Steps have been used in various use cases such as home automation and business workflow automation. For instance, using tabs, people can create a rule to open their smart windows automatically whenever the temperature is above a certain threshold. In this work, we focus on tab from IFTTT because first, it has large user base, and second, the database is publicly available. However, we believe that our study can generalize to other platforms as the general idea of tabs is similar across different platforms. This is an example of tabs in IFTTT. A tab is composed of two main parts. The first part is the trigger, the second part is the action. Each trigger and action has a channel. Each trigger and action also has a function. A function is equivalent to an API. Lastly, each trigger and function also has a set of fields or parameters. In summary, we can decompose tab into three different granularities, namely channel, function, and field. Although it looks easy, composing trigger action programs can be challenging because of the large search space when choosing trigger and action components. Because of this large search space, users most likely may not know all the available services and functionalities. These are the prior approaches that try to tackle tab generation problem. The current SOTA approach is LAMP. The simplified architecture of LAMP is shown by the figure in the current red box. The first drawback of LAMP is it yields bad performance if the input description is unclear. Unclear description is a description that doesn't describe the target channel or functionality. We believe that the bad performance is because LAMP cannot leverage the implicit relationship between the predicted trigger and action components. The prediction of each classifier in LAMP is obtained by conditioning the probability of Y on the input description only. The second drawback is it doesn't scale well. From the architecture, we can see that the number of predicted components depends on the number of classifiers. To overcome the aforementioned limitations, we approach the problem as a sequence learning problem. We believe that formulating the problem as a sequence learning can allow the model to learn the implicit relationships between the predicted components. The example in the slide demonstrates that the model also takes the prior predicted components into account when predicting the action channel. The second advantage is our approach is more scalable because the number of components does not depend on the architecture. Based on the previous problem formulation, we propose RecipeGain, a deep learning-based approach that adapts transformer sequence-to-sequence architecture to address tab generation problem. Inspired by the fact that the input description resembles a general English language, we boost the performance of RecipeGain by instantiating the encoder's weight using a pre-trained model. For the experimental setting, we trained three variants of RecipeGain, namely RAN-to-RAN, probe-to-RAN, and code-to-RAN. Both encoder and decoder are randomly initialized in RAN-to-RAN, while probe-to-RAN leverage Roberta to initialize the encoder's weight. In code-to-RAN, we replace Roberta with CodeBird. We use LAMP as the baselines, as it is the current SOTA approach. We perform the experiment on two granularities, function level and field level. For the field level experiments, we don't compare LAMP because it is not designed to generate the field component. For the metrics, we use mean reciprocal rank and BLEU score. This is the statistics of each training, validation, and test sets. For the test sets, Gold 15 and Noisy 15 are from the prior studies, and both are annotated by human. Gold 15 contains tabs with the clear descriptions, while Noisy 15 contains tabs with the unclear descriptions. On the other hand, test plus field is created using stratified random sampling strategy. This is the result of function level evaluation. From the figure, we can observe that lamp, which is indicated by the black bar, is consistently lower than recipient. We can also observe that the performance difference between rope to rent and code to rent are small. We confirm that the differences are not statistically significant. This table shows the relative improvement of rope to rent and code to rent against LAMP and rent to rent. We can observe that the improvement of recipient against LAMP is significant in the noisy 15 test set. In other words, recipient is more robust against unclear descriptions than LAMP. From this table, we can also observe that the improvement of leveraging pre-trained model is significant in the limited data setting. We can observe that the improvement is big when the model is trained using week 15 data. On the contrary, the improvement is small when the model is trained on the bigger dataset. This is the result of the field level evaluation. We can observe that leveraging a pre-trained model can improve the performance further by 3.3 until 3.9%. In conclusion, first, we frame type generation as a sequence learning instead of classification problem. Second, we propose recipient, a deep learning-based approach that adapts transformer and leverages a pre-trained autoencoding model to instantiate the encoder's weight. Our experiment results demonstrate that recipient can outperform prior based approach by significant margin. That's all from me and thank you for your attention.